An electron is not a thing. I know that sounds absurd. You can detect electrons, you can measure their charge, their mass, their spin, you can count them, you can use them to build circuits. How can they not be things? But they're not in the way you think. An electron is not a tiny ball flying through space. It's not a particle with a definite position and velocity. It's not a localized object that exists at one place at one time. An electron is a quantum object, and quantum objects do not behave like anything in your everyday experience. They are not waves. They are not particles. They are something else entirely. Something that has no classical analog, something that breaks every intuition you have about how reality works. I'm Leonard Susskind. I've spent 50 years working with quantum mechanics, teaching it, using it to make predictions that match experiments to extraordinary precision. And I can tell you with complete confidence, quantum mechanics works. It's the most successful theory in the history of physics. We've tested it billions of times. It's never been wrong. But it's also the most disturbing theory in physics, because it says that at the fundamental level, reality does not work the way it appears to work. Objects don't have definite properties until you measure them. Particles exist in multiple states simultaneously until you look. The act of observation changes what you observe in ways that have nothing to do with the clumsiness of your instruments. Quantum mechanics breaks reality. Not approximately, not in some edge case. Fundamentally, at the level of individual particles and atoms. And nobody, not Einstein, not Bohr, not Feynman, not me, fully understands what it means. Let me show you why. Starting with the experiment that reveals the strangeness most clearly. The double slit experiment. Take a barrier with two narrow slits cut in it. Behind the barrier, place a screen that detects where particles hit. Now fire electrons, one at a time, at the barrier. If electrons were classical particles, tiny balls, they would go through one slit or the other. You'd see two bright bands on the screen, one behind each slit, corresponding to the electrons that made it through. But that's not what happens. What happens is this. Electrons build up an interference pattern, bands of bright and dark regions, alternating across the screen. This is the signature of waves interfering with each other. When two waves overlap, they can add constructively bright bands or destructively dark bands. Water waves do this, sound waves do this, light does this. But electrons are not waves, they're particles. We detect them as individual clicks on the screen, one at a time. They arrive at specific points, not spread out like a wave. So how can individual particles create an interference pattern? Here's the answer quantum mechanics gives, and it's deeply unsettling. Each electron goes through both slits simultaneously. Not one or the other, both. The electron is in a superposition, a quantum state, that's a combination of went through the left slit and went through the right slit. This superposition interferes with itself. The two parts of the electron's quantum state combine, creating the interference pattern. But here's the really strange part. If you put a detector at the slits to see which one the electron goes through, the interference pattern disappears. You get two bright bands, just like classical particles. The act of measuring which slit the electron went through changes its behavior, not because you disturbed it mechanically, because measurement collapses the superposition. The electron is forced to choose one slit or the other, and once it's in a definite state, there's nothing left to interfere. The interference pattern vanishes. This is not hypothetical. This experiment has been performed thousands of times with electrons, photons, atoms, even molecules made of hundreds of atoms. The result is always the same. Quantum objects exist in superpositions. Measurement collapses the superposition. The act of observation changes the outcome. Now let me make this even more bizarre. The delayed choice version Perform the double slit experiment. The electron passes through the slits, but before it hits the screen, you randomly decide after the electron has already passed through the slits whether to measure which slit it went through or let it interfere. If you measure, you get particle behavior, no interference. If you don't measure, you get interference. Your choice, made after the electron passed through the slits, determines which state the electron was in when it passed through the slits. The future measurement affects the past state. Not because information traveled backward in time that would violate causality, but because the electron wasn't in a definite state until you measured it. It was in a superposition. And which basis you measure it and which question you ask determines which answer you get. The electron's past is not fixed until you observe it. And what you observe depends on what you choose to measure. This is not philosophy. This has been tested experimentally. The delayed choice double slit experiment confirms it. Quantum mechanics says the past is not fully determined until measurement occurs. And that breaks our entire picture of how time and causality work. Now, let me tell you about superposition more carefully, because this is the heart of quantum mechanics and the source of all its strangeness. In classical physics, a system is in one state, the ball is either here or there, the switch is either on or off, the electron went through the left slit or the right slit, definite, determinate. Real. In quantum mechanics, a system can be in a superposition of multiple states. The electron is in a state that's part here and part there. The atom is in a state that's part excited and part ground state. The particle is in a state that's part spin up and part spin down. This is not uncertainty about which state it's in. This is not ignorance. The system is genuinely in both states simultaneously until you measure it. The superposition is the real state. It's described by the quantum wave function, a mathematical object that encodes all possible measurement outcomes and their probabilities. When you measure the system, the wave function collapses. The superposition disappears. The system is forced into one definite state. Which state? You can't predict with certainty. Quantum mechanics only gives you probabilities. If the wave function says there's a 70% chance of finding the electron here and a 30% chance of finding it there, then you'll find it here 70% of the time and there 30% of the time if you repeat the experiment many times. But on any individual trial, the outcome is random. Not because you don't know something, not because there are hidden variables you haven't measured. The outcome is genuinely, fundamentally random. Einstein hated this. He said, God does not play dice with the universe. But every test we've ever done says, yes, at the quantum level, the universe is fundamentally probabilistic. Outcomes are not determined until measurement happens. This leads to the measurement problem. And it's the biggest unsolved problem in the foundations of quantum mechanics. The problem is this. The wave function evolves smoothly and deterministically according to the Schrödinger equation when you're not measuring it. Superpositions remain superpositions. Interference patterns build up. Everything is linear and predictable. But when you measure the system, something different happens. The wave function collapses. The superposition vanishes. The system jumps into one definite state. This collapse is nonlinear, random, and instantaneous. What causes the collapse? When does it happen? Why does measurement behave differently from every other physical process? Nobody knows. This is the measurement problem. And there are several proposed solutions, none of them fully satisfactory. The Copenhagen interpretation, developed by Niels Bohr and others, says measurement is fundamental. The quantum system evolves according to the Schrödinger equation. The measurement device is classical. When they interact, collapse happens. But this raises the question, what counts as a measurement? What's the boundary between quantum and classical? Where do you draw the line? The many worlds interpretation? proposed by Hugh Everett, says there is no collapse. The wave function always evolves according to the Schrodinger equation. When you measure a system in superposition, you enter a superposition with it, the measurement device, and you split into multiple branches. In one branch, you see the electron here. In another branch, you see it there. Both outcomes happen, both are real, but they're in different branches of the wave function, unable to interfere with each other. This sounds crazy, but it takes quantum mechanics seriously and doesn't add collapse as a separate process. The cost is an enormous ontology, infinitely many branches, all equally real, splitting every time a quantum measurement happens anywhere in the universe. There are other interpretations. Objective collapse theories add a physical mechanism that causes wave functions to collapse spontaneously when systems get large enough. Pilot wave theory says particles have definite positions guided by a wave that obeys the Schrodinger equation. Each has strengths and problems. But here's what they all agree on. The classical picture of reality objects with definite properties existing independently of observation is wrong at the quantum level. Something fundamentally different is happening. Let me make this concrete with Schrödinger's cat. This is not an experiment anyone actually does. It's a thought experiment designed to show how absurd quantum mechanics sounds when applied to everyday objects. Put a cat in a sealed box. Inside the box, there's a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers, breaking the vial and killing the cat. If the atom doesn't decay, the cat lives. Radioactive decay is a quantum process. After one half-life, the atom is in a 50/50 superposition of decayed and not decayed. According to quantum mechanics, before you open the box and look, the atom is in superposition. And because the atom's state is entangled with the detector, and the detector with the vial, and the vial with the cat, the entire system is in superposition. The cat is in a superposition of alive and dead. Not either alive or dead and you don't know which. In superposition, both simultaneously. Of course, when you open the box, you see a definite outcome. The cat is either alive or dead, not both. The superposition collapses, or, in many worlds, the universe splits into one branch where you see the cat alive and another where you see it dead. Schrödinger proposed this to show how ridiculous quantum mechanics seemed when applied to macroscopic objects. But the point is, quantum mechanics doesn't provide a clear boundary. It doesn't say quantum rules apply to atoms but not to cats. It says superposition and collapse apply to everything, which means either cats can be in superposition, which is absurd, or something new happens at macroscopic scales that we don't understand. This is the measurement problem, and it's not solved. Now let me tell you about entanglement, because this is where quantum mechanics gets even stranger. Two particles can become entangled. Their quantum states become correlated in a way that has no classical analog. Measure a property of one particle, and you instantly know the corresponding property of the other, no matter how far apart they are. Einstein called this spooky action at a distance. He thought it proved quantum mechanics was incomplete. But John Bell showed you could test whether entanglement is real or whether particles carry hidden information. The tests have been done. Entanglement is real. The correlations are instantaneous and cannot be explained by any local hidden variable theory. What this means is profound. Two entangled particles are not two separate things. They're one quantum system described by a joint wave function. Measuring one particle changes the joint state, which immediately affects what you'll measure for the other particle. Not because a signal traveled between them faster than light signals are impossible, but because they were never truly separate. They were always one entangled system. This is non-locality, and it's a feature of quantum mechanics, not a bug. Objects that have interacted in the past remain correlated even after they've separated. Their properties are not independent. The whole is not reducible to the sum of its parts. Let me tell you what this means for reality. Classical reality is local and deterministic. Objects have properties whether you measure them or not. Those properties evolve according to laws. If you know the initial conditions precisely, you can predict the future with certainty. Objects in different locations are independent unless a signal passes between them. Quantum reality is non-local and probabilistic. Objects don't have definite properties until measured. The wave function evolves deterministically, but measurement outcomes are random. Objects can be entangled across arbitrary distances with correlations that have no classical explanation. Quantum mechanics says the world is not made of things with properties. It's made of wave functions evolving in Hilbert space. And wave functions are mathematical objects, complex valued functions that encode probabilities of measurement outcomes. They're not physical objects in space. They live in an abstract mathematical space with far more dimensions than the three spatial dimensions we see. What we call particles, what we call positions, what we call properties, these are all emergent from the wave function when measurement happens. But the wave function itself is the fundamental reality, and it's nothing like what we experience. This is why quantum mechanics breaks reality. Reality, as you experience it, is a projection, a shadow, a classical approximation of an underlying quantum state that has no classical analog. Here's what keeps me up at night. Quantum mechanics works. We've tested it to absurd precision. The predictions match experiments to 1 part in a trillion. Every piece of modern technology, computers, lasers, MRI machines, GPS, depends on quantum mechanics being correct. It's not wrong, but we don't understand what it means. We don't know what the wave function is. We don't know why measurement is special. We don't know where the boundary between quantum and classical lies. We don't know which interpretation is correct, or if all of them are wrong and the truth is something we haven't imagined yet. Quantum mechanics has been the foundation of physics for a century, and we still don't know what it's telling us about reality. Maybe the wave function is real and everything else is emergent. Maybe many worlds is correct and every quantum event splits the universe. Maybe there's a deeper theory beneath quantum mechanics that will make sense of it. Maybe observers play a fundamental role in collapsing the wave function. Maybe consciousness is involved. Or maybe reality just doesn't work the way we think it should. Maybe the universe is fundamentally probabilistic, fundamentally non-local, fundamentally strange at its deepest level. Maybe our intuitions built from macroscopic experience are simply wrong when applied to atoms and photons and electrons. I think the last option is most likely. The universe doesn't owe us an intuitive explanation. It doesn't have to make sense in terms of everyday experience. It just has to be consistent with the mathematics and the experiments. And the mathematics says superposition is real, entanglement is real, wave function collapse is real, measurement changes outcomes, the observer matters. Reality at the quantum level is not what it appears to be. Quantum mechanics works, but it breaks every assumption about how reality should work, and after 100 years we still don't know why.